couple minutes on scientific notation. What is that? So scientific notation is a way of describing either very large numbers or very small numbers in a more a useful way. So here is the idea. We want to take advantage of a unique property of our number system, which is a base 10 number system. Why is it a base 10 number system, you might ask? Well, because there's only 8 unique characters that you had to learn how to write all our numbers, right? Here they are. 1, 2, 3, 4, 5, 6, 7, 8, and 9, right? Here are 9 pictures that you needed to learn how to, 10 pictures that you needed to learn how to draw. 1 through 9, and then there's the 0. So all you have to do is learn how to do those. To get to the next number, right, as we're describing, as we're thinking, here's 1 apple, here's 2 apples, 3 apples. How do we describe 10 apples? Well, we could have come up with a whole new squiggly description of it, right? Maybe I invent my own numbers, and my own numbers say that this guy is 10, and that this guy is 11, and that this guy over here is 13, right? I could start inventing new squiggly things to represent the rest of the numbers, but then that would get really difficult. For one thing, where am I going to stop? Am I going to come up with a new kind of picture to represent every single number? That's going to get crazy, right? And 2, are you going to have to memorize every one of these little symbols so that I can quiz you? What was the picture that represented 27? You're like, oh, it was the one with this thing and that. That's 27. Okay, well that could get really ugly, right? So one of the great advantages of our number system is that some amazingly clever person decided that instead of coming up with a brand new squiggly picture to represent the next value, why not recycle the ones we already have where the order makes a difference? So we decided that the next one is going to recycle these 2. And the one after that is going to repeat that one. And the one after that is going to recycle this one and that one. Right? But we're not learning a new picture. We're using the same symbols to put them in a different order, repeat them, or put them in the order matters. So that this is a different number from this one because we know that the order matters. Right? So that plus the decimal number, right? We throw in a decimal and we know that we can describe really any number in the real number system. So it greatly gives us an ability to describe, say, that over that. All we need is to learn how to draw 10 different symbols and throw in a decimal, and that's all we need to learn as far as the handwriting or the symbols. Then we just got to understand their place, right? The order in which they're written matters. Good? Can you imagine a number system where the order didn't matter? Like this number and this number both represented the same thing? Well, that could get confusing, right? It would be a whole new thing to have to adjust to. But we could do it. But our system is better. So that's why it's a base 10 number system, because there are 10 symbols that we use to represent our numbers. And because it's a base 10 number system, there's something curious that happens with powers of 10. That's pretty nice, and we want to take advantage of it. So think about 10 to the power of 0. What is that equal to? 1. We already said any number raised to 0 is 1. 10 to the first power is just 10, of course. What about 10 squared? 10 times 10, which is equal to 100. 10 to the third power is 10 times 10 times 10 times 10. Oops, I went too many. Got excited. 10 times 10 times 10, that's going to be 100 times 10, which is 1,000. Good. And then 10 to the fourth power, 10 times 10 times 10 times 10. Okay, so that guy right there is 100. And then you get 10 people to give you $100, you get to 1,000. And now you have 1,000 times 10 is 10,000. And so a really nice pattern begins to appear between the powers in the exponent and the number of zeros. There were two there and 2 zeros, and 3 there and 3 zeros. So it's a nice little pattern that we can use. So we don't really have to do this part in the middle and actually multiply. if I wanted to express 10 to the power of 7, I know that's just a 1 with 7 zeros behind it. 1, 2, 3, 4, 5, 6, 7. Good? Okay, well that's equal to 10 million. Okay, a pretty big number by some standards, but we can express even larger numbers, right? If we wanted to express 10 to the power of, 13. Well, that's a really big number. That's 1 with 1, 2, 3, 4, 6, 7, 8, 9, 10, 11, 12, 13. It's a lot of zeros, right? So that's just cumbersome, right? To have to write that all the time. It's just a lot easier to say 10 to the 13th power than 1 with, all those zeros in there. Good? Questions so far? Okay, that's when we grow in this direction and we make the exponents bigger integer values. And then let's look at the other direction. What if, let's tie it in here in this direction. Okay, that's right. What if we had 10 to the negative 1 power? What is that equal to? Negative in the exponent, we flip it underneath 1, that becomes 1 over 10, which is 0.1, 1/10. And then 10 to the negative 2 power, 1 over 10 squared, which we know is 1 over 100, which is 0.01. 10 to the negative 3 is 1 over 10 to the third power, which is 1 over 1,000, which is equal to 0.001. Okay, so now we can start to see a pattern that starts to emerge. So rather than thinking about adding zeros like we did here, okay, it's a 1 with 2 zeros, it's a 1 with 4 zeros. Rather than thinking about adding zeros, it might be better if we think about it as starting with the number 1. We start with the number 1, which has a decimal right in there. And we think about how many spaces we move the decimal over as the pattern. So here, if we want 10 to the second power, we would move this decimal over 2 spaces, which means we add 2 zeros. So 10 to the second power is equal to 100. On the other hand, if we start with this, and we want to know what is 10 to the negative 4 power, 10 to the negative 4 means that we got to move the decimal over to the left by 1, 2, 3, 4. So that'll be this. We need to add 3 zeros if we want that. So 10 to the negative 4 is equal to 0.1231. Okay? So 10 to the positive 4 was a 1 and we add 4 zeros. But 10 to the negative 4 means we really only add 3 zeros to the left of the 1, then the decimal, and then write it this way. Good? Any questions? No? Okay, so these properties of 10 make it nice for us to express very large numbers that start with a 1 and have a bunch of zeros, or very small numbers that start with a decimal, 0, 0, 0, a bunch of zeros, and then end in a 1. So that's nice. If that's all we ever had to deal with is numbers that look like that, then it would be great to just express in this way. But of course, we have other numbers we deal with. So think about this. If I had 1,250,000, how many different ways can I express this and break it down into the multiplication of two numbers where one of those numbers was one of these powers of 10? So in other words, what I could do is think about this as 125,000 times 10, right? Think about what that is. So 1,250,000 is the same thing as 125,000 times 10. If you can get 10 people to lend you 125,000 each, you would have 1,250,000, right? Okay, another way to think about it is that maybe it's 2500 times 100. All right, what does that mean? Okay, well, if you want to be a millionaire, all you got to do is get 100 people to lend you $12,500 each, and then together you get $1,250,000. Do you guys think you can get 100? Do you know 100 people that will let you have $12,500 each? Probably not. Okay, well, let's keep going here. So maybe it's 1250 times 1,000. To be a millionaire, all you got to do is get 1,000 people, each of those people, to lend you $1,250. Can you do that? Getting closer? Maybe? All right, let's keep going. 125 times 10,000. Can you get 10,000 people to each give you $125? Maybe, maybe. Okay, this times this equals to 1,250,000. Let's keep going. Well, so far I've been kind of knocking down the zeros, but really what I've also been doing, you can think of it as moving the decimal over. So this is also equal to 12.5 times 10. Right, so 1, 2, 3, 4, 1, 2, 3, 4, 5 now. So, okay, to become a millionaire, all you have to do is get 100,000 people to each let you have $12.50. No? Maybe? You gotta get 100,000 friends on Facebook and you know, send them all a, hey, can I borrow 12 bucks? $12.50? Boom, instant millionaire. No? All right, well that might be a lot of money. How about $1.25? 1.25 times 1 million. Can you get 1 million followers to each give you $1.25? Seems a little more doable, doesn't it? Good, maybe? All right, let's do one last one. How about 0.125 times 10 million? So in other words, in order to get 1,250,000, you got to get 10 million followers on Facebook to each give you 12 pennies. That's not bad, right? Can you, if someone you barely knew said, hey, can I borrow 13 pennies? You'd probably, if you had it, right? Here, it's just change in my pocket, and I don't care. Here. I don't know that I would lend anybody $1,250. That would be hard. I'd have to like really know them really well to lend them $1,200, right? Like I have to know where they live, I have to know where they work, I have to know I'm getting my money back, right? 125, you know, that's, I don't know. But 13 pennies, I would lend that to somebody. So it might be easy to convince people to give you 13 cents, and all you have to do is convince 10 million people to give you 13 pennies each. I'm rounding up. And then you'd have more than that, right? So 0.125 times that is equal to this. Okay, so in each of these cases what we've done is we've rewritten it as a base number times something that's a power of 10. So, well this one's pretty obvious, but this one for instance can be written as 12500 times 10 to the second power. This one can be written as 1250 times 10 to the third power. This one can be written times 125 times 10 to the fourth power. This one can be written as 12.5 times 10 to the fifth power. This one is 1.25 times 10 to the sixth power. And then finally this one is 0.125 times 10 to the seventh power. Okay? Good, good, good. Okay, I know you're thinking, well, why would anybody do any of those crazy things? Why don't you just write down this number? Okay, keep in mind that right now this number is really not that big. If I started going really crazy and adding a bunch of numbers over there, a bunch of zeros, I can add 9, 10, 12, 20 zeros. It could get really crazy. Whereas this, if I want to represent a much larger number, it just changes this little number in the exponent, so it makes it easy to write down a really big number. Okay, so all of these are correct. All of them represent this quantity up here. But for the sake of consistency, so that we're all on the same page and we all represent this number in the same way, we got together and agreed on a format. And the format says that we're going to rewrite a number as the multiplication of two parts, where one part is a power of 10 and the exponent is a counting number, positive or negative, and the other number is a number that is between 1 and 10, if it's a positive number, including the 1, not the 10, or if it's a negative number, it's between negative 10 and negative 1, again, not including, including the negative 1. So in other words, it's a number that lands here. Here's 0, here's 1, here's 10. I'm looking for a value that lands in between here. A number that is either a 1 or anywhere in here, but we don't let it be 10. So this number does not land in that part of the number line. Neither does that one, neither does that one, neither. Here it is. This is the only one that satisfies that condition. 1.25 is right here. 1.25. So this is the one that qualifies as being written in scientific notation. They're all correct, but this is the only one that can be said to be in scientific notation. Got it? Good. So we need this number in here to land between 1 and 10, not including the 10, but potentially including the 1. And now if it's a negative number, if we were talking about negative 1,1,250,000, then it would be a number that's over here. So like here is negative 1, and let's say over here is negative 10. So it's a number that is maybe negative 1, and anything that lands in there up to, but not including negative 10. So a number that lands in there. We need this front part of the scientific notation value to land in those blue zones. Any questions? So if we had 3.462 times 10 to the 5th power and we wanted to expand that out, that means that we got to move the decimal over to the right. We got to multiply 3.465 times 100,000, right? 1 with 5 zeros is 100,000. Or we got to move the decimal over to the right by 5 spaces. What's our final answer going to be? What's it going to be? 3.462 times 10 to the 5th power.
346,200?
Mm-hmm. 1, 2, 3, 4, 5. 100,000. So this is going to be 3.462. We move the decimal over 1, 2, 3, and then we have to add 2 zeros. So the answer is 346,200. Right, that's the expanded form. What about the second one? We have 7.38 times 10 to the negative 4 power. Okay, so because it's a negative, I know that this is times, and this is 0.123, right? We move the decimal over 4 spaces that way, so 1, 2, 3, 4. So we add 3 zeros between the decimal and the 1. And so I know there's going to be a small decimal answer. And the pattern is going to be to move this guy over to the left 4 spaces. So I'll end up with 0.123738. And so because it was a negative 1, I knew that this moved over 1, 2, 3, 4 spaces. So my final answer is 0.000738. Good? Questions, 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 questions? Okay, almost done. Let's go in the other direction. What if you were given a very large number like this one, right, similar to the one we did a minute ago, and we wanted to write it in scientific notation? So we got to count the number of decimal spaces that we need to move. Right, so how many decimal spaces do we move in? 6, 2, 5, 7, 1, 2, 3, 1, 2, 3. So the decimal place originally lives back here. So it's 1, 2, 3, 4, 5, 6, 7, 8, 9 spaces. So in scientific notation, this is 6.257 times 10 to the 9th power. Notice that I stopped there because this is the number that lands between 1 and 10. If I had stopped there, it would be 62. That doesn't land between 1 and 10. And if I kept going by 1 more, it would be 0.6. That doesn't land between 1 and 10. Okay. The last one here is 0.000, how many zeros? 4, 5 zeros? 721. 1, 2, 3, 4, 5, 7, 2, 1. Okay, so we got to figure out how to rewrite this in scientific notation. So I got to start counting again. 1, 2, 3, 4, 5. I moved the decimal over 6 spaces. So I know it has something to do with the power of 6. 7.21. I know to stop there because this is a number that lands between 1 and 10. Right? If I stopped over here, it would be 0.721. That doesn't land between 1 and 10. And if I kept going one more, 72 is not a number that lands between 1 and 10. So I knew I had to stop there. Times 10 to the power of, and now this is the most common mistake people get. Right? They write a 6 there because they moved it over 6 spaces. But think about it. This would make it a very big number. So 7 times a very big number is going to be this tiny little decimal. That doesn't make sense. So if you just take a minute and think about it, you'd recognize that that must mean that it's got to be a negative. That makes this a very tiny little decimal, and a tiny decimal times a 7 might be equal to that one. Okay? So this is the scientific notation way of describing those numbers. Good? Good.